Hi, everyone. Welcome to another PDX Duck Science Night. We are so happy you could attend our second Science Night of 2021. We're happy to be a part of this year's Portland Rose Festival as a broadcasting and porch parade sponsor. The PDX Ducks are a dedicated board that strives to engage, support, and maintain connections with local ducks in the Portland community. Make sure you're checking your emails and following us on social media to keep up to date with everything we are doing. Thank you again for continuing to show up virtually during these unprecedented times. Hopefully the next time that we come together, it'll be in person. So we're going to be taking questions. So use the Q&A function to submit any questions for Diego. And we're also going to be doing a drawing at the end for two $20 gift cards to the duck store using random name generators. So just make sure to hang out until the end in case your name is called.
Great. Thank you, Ellie. It is my pleasure to introduce our featured speaker for this evening. Dr. Diego Melgar is the Anne and Lou Williams Chair of Earth Sciences and an assistant professor of geophysics in the Department of Earth Sciences at the University of Oregon. His research focuses on large earthquakes. He works on understanding the physics of faults using many diverse kinds of onshore and offshore data. He researches the hazards associated with these large events, working on tsunami modeling and coastal impacts, as well as studying how strong shaking can be forecast. Professor Melgar was awarded the 2016 Charles Richter Early Career Award from the Seismological Society of America. He is also a member of the National Academy of Sciences Committee on Solid Earth Geophysics. Prior to joining the University of Oregon, he spent 3 years at the University of California, Berkeley's Seismological Laboratory. He earned his Bachelor of Engineering in Geophysics from the Universidad Nacional Autónoma de Mexico and has his MS and PhD in Geophysics from the Scripps Institution of Oceanography. Dr. Melgar, welcome to Portland Science Night.
Thank you, Sandy. Can you see my full screen slides right now?
Yes, we can.
Okay, so let's get this show on the road. Thank you, everybody, for showing up today. And I will take you on a tour of the Pacific Northwest and of the great earthquakes that we know occur here, offshore Washington, Oregon, California, and British Columbia. Again, please use the Q&A function there at the bottom if you have any burning questions that you want to ask. Okay, so most of you, well, if you're a longtime citizen of the Pacific Northwest, you knew this already, but for many people, the awakening, as I call it, of big earthquakes in the Pacific Northwest really came with this article in New Yorker magazine back in 2013. Catherine Schultz was awarded the Pulitzer Prize for this. She said in that article, quoting experts, scientists, and emergency managers, that we now know that the odds of a big earthquake magnitude 8 are about happening in the next 50 years are roughly 1 in 3. The odds of the really very big one are about magnitude 9 are about 1 in 10. And of course, this I prepared this talk for other people outside of here. So most of you know that when I say Cascadia, I mean the Pacific Northwest. So what I'm going to talk to you about today are these 3 things. How do we actually know that these big earthquakes happen in the Pacific Northwest? It's probably one of the most beautiful science stories that we have in seismology and geology. It wasn't always obvious that big earthquakes happen here. I'm also going to talk about, once these big earthquakes happen, what is it that we can expect across our region. But because I don't like to just be the bummer always all the time, I'm also going to finish with, now that we have this knowledge, what can we do? How can we arm ourselves and protect each other when these big earthquakes happen? So these are the 3 topics that I'm going to cover today. So first, we're going to talk about how do we actually know that this is possible here in the Pacific Northwest. In order to situate you, I want to talk a little bit about faults and what makes a big earthquake a big earthquake. You're looking here at a picture of a recent fault that broke in 2016, well, fairly recent, in New Zealand. This is a very famous, at least in seismology circles, Kaikoura earthquake. And you can see for scale, these 2 researchers there standing at what we call the fault scarp, measuring the offsets, the motion between these 2 sides of the fault. These faults could be traced for miles and miles and miles and miles. Big earthquakes are pretty big. So what is sketched out here on the left-hand side in these blue rectangles are the sizes, more or less, of the faults that make earthquakes of different magnitudes. So this M6.1, M6.9, M7.2, that's the magnitude of the event. For any of you that have any kind of background or roots in California, some of these earthquakes might be familiar. The 2014 Napa earthquake was a magnitude 6.1. The fault that made that earthquake broke about 20 miles of the Earth's crust. Meanwhile, for the 1989 Loma Prieta earthquake, this is the very famous World Series earthquake, game 2 or game 3, I forget, of the World Series between the Oakland A's and the San Francisco Giants. This earthquake happened in the middle of that game. That almost magnitude 7 earthquake breaks about 40 miles of the Earth's crust. In 2010, when I was in graduate school, a very famous magnitude 7.2 on Easter Sunday broke about 80 to 100 miles of the Earth's crust at the US-Mexico border. So those numbers are pretty big. 100 miles for an earthquake seems like a really long distance for a fault to break. However, when we talk about our very famous Cascadia earthquake, those faults from California, I've rescaled them now to 100 miles. What we're talking about for these very big earthquakes in Cascadia pales in comparison. It's so much larger than the big earthquakes in California, because our earthquakes here in the Pacific Northwest are really, truly large. So this is the approximate size of what we would expect for a Cascadia earthquake. 500 miles, 600 miles of fault breaking. That's a really long distance. And that's not uncommon for these really large earthquakes. When we compare what we think we know about the 1700 magnitude 9 Cascadia earthquake to other recent large earthquakes, this is how it stacks up. In 2004, many of you will remember the Sumatra earthquake. This was in Indonesia. This was a magnitude 9.2-ish earthquake that killed 250,000 people. That earthquake broke almost 1,000 miles of the Earth's crust. Imagine that, 1,000 miles of the Earth's crust breaking in about 5 minutes worth of time. So the message I want you to take away from this is that these large earthquakes are not nothing. They're incredibly large releases of energy that happen over just a few minutes of instance in the Earth's crust. Now, again, coming back to this article in New Yorker, most seismologists already knew about this, but it really took Catherine Schultz in a beautiful written piece in New Yorker magazine to transform the public's imagination and really bring forward this notion of these really big earthquakes. In this article, she quotes Kenneth Murphy from FEMA's Region 10, which is our region, saying that once an earthquake like this happens, our operating assumption is that everything west of Interstate 5 will be toast. Now, from what I gather, Ken Murphy got in a lot of trouble for saying something like this. It was, by some, said it was alarmist that he said this, because if you look at the area west of Interstate 5, that is here, it's a pretty big area. It spans almost 600 miles north to south and about 60 miles east to west of Oregon, Northern California, Washington, and well into British Columbia. So was he really that alarmist is what I want to talk about today. So here's some science background of where we are. Cascadia, the Pacific Northwest, Oregon, Washington, and California are what is known as a subduction zone. And that's what is shown here in this animation, in this cutaway. We live up here. These are our volcanoes. And what is happening is this continental plate on the right-hand side is crashing against this oceanic plate on the left-hand side. It's usually stuck here, but every now and then that energy gets released every 200, 300, 400 years. And when that energy gets released, it takes the shape of tsunamis and it takes the shape of strong shaking. And that's what a subduction zone looks like, and that is where we live. That's where I am right now in Eugene. I'm right about here, just west of the Cascades, east of the coast, somewhere around here, above this region that is capable of making these biggest earthquakes. Now, truly the beautiful aspect of our region, and seismologists often wax poetic about subduction zones because the sizes of these things boggle the mind so much that we marvel that anything like this is even possible. We look at other planets in the solar system. We hear so much about Mars and Venus and NASA and SpaceX going to other places. These earthquakes don't happen in any of the other planets. They seem to only happen here on Earth. Now, what is special about Cascadia is that when you compare it to other subduction zones, these happen all over the world, in Chile, Japan, Mexico, and in Alaska, like on this map. These subduction zones are characterized by frequent earthquakes. People, denizens of these places, feel earthquakes underfoot all the time. What is shown in this picture is 30 days of small magnitude earthquakes, magnitude 2.5 and larger. You will barely feel a magnitude 2.5, but over 30 days, there will be hundreds of them all across this subduction zone. It's really, really very obvious that you live in a subduction zone just because you will feel little tremors weekly, bi-weekly, every month. You will feel something to remind you that the earth under your feet is unstable and capable of making these big earthquakes. However, when we look at that same 30-day period for the Cascadia subduction zone, for us, we see almost no earthquakes. Cascadia is very peculiar amongst worldwide subduction zones in that it doesn't seem to make a lot of these small magnitude events. And this is the reason why in the mid-80s, early 90s, mid-90s, seismologists and geologists were in a big argument as to whether Cascadia was really a subduction zone or whether it used to be a subduction zone, but it was no longer active. So if you were an academic or a researcher back then, 20 or 30 years ago, that would be the kind of debate that you would be engaged in. And it would be because of this. There's almost no earthquakes there. So how do we actually know? How did we actually find out or figure out that this is true, that Cascadia is capable of making these big events? Well, it turns out that to do that, we need geology. And this is what a geologist looks like. He is a very famous geologist. His name is Brian Atwater. He works at the USGS office up in Seattle. And he's pointing at this line, this contact between this white colored unit and this dark colored unit as evidence that there must have been big earthquakes in Cascadia's past. How? How did he know this? Well, what he figured out is as he walked up and down Cascadia is that what this is right here, this used to be a marsh. And now this marsh that used to be full of bushes and forests is overlain by things like sand. So how could that be? What he reasoned was that after the earthquake, what used to be the marsh suddenly dropped by about 2, 3, 4, 5, almost 6 feet during the earthquake. And after it dropped, the tsunami came ashore and deposited these sands. And this thing that used to be a marsh was killed. It died. And then more deposits were placed on top and the marsh grew anew. This is a peculiar observation if you see it in one place, but what Brian and other geologists did is walk up and down Oregon, Washington, California, and British Columbia, and they repeatedly found evidence that marshes had subsided and died and disappeared and were recolonized by these other sediments on top. And perhaps the best way in which this is expressed is by the very famous ghost forests. For those of you that have been here a while, you will have heard about these. This is in Capellas in Washington. This picture right here on the left is taken here, over here in this meander in the river. And what you can see is these trees used to be alive and are now dead. And you can see these ghost forests all over the Pacific Northwest. And what Brian reasoned that had happened is that during these episodes, during these big earthquakes where the land just suddenly drops 2 or 3 meters, what happens is that these forests that are made up of red cedar trees and Sitka spruce trees, these forests that are usually above land subside beneath the tidal level and are all of a sudden overcome by salty, we call it brackish water, and the trees cannot live in salt water. They were designed to live on fresh water. So once they subside and are submerged in the salty water, they all die. So Brian started to find these ghost forests, unexplained at first, but when he looked up and down Cascadia, he found these ghost forests were in Northern California. They're, of course, in Oregon, they're in Washington, and they're in British Columbia. So the fact that he was finding these ghost forests all over the place was a very key piece of evidence to suggest that something big must have happened. What can make the land subside by 6 feet over 600 miles of Cascadia subduction zone? Only a large earthquake. Now, the other key piece of evidence came in the early 2000s, and this is work mostly done out of Oregon State University. They went offshore. Instead of looking on land, they went offshore, and at all of these great and Y dots, they looked for evidence of underwater landslides. These are called turbidites. Underwater landslides, as you can see this video in a lab on the left-hand side, happen because they're shaking. The shaking dislodges the sediment in these very steep canyons over here, and these pulses of sediment travel down the slopes, much like a landslide, but because the sediment is suspended in the water, it travels for a really long way. And you can see evidence of these underwater landslides hundreds of miles down the slopes of these canyons. And when people went to look for these landslides, again, they found them everywhere. They found them offshore the Olympic Peninsula. They found them offshore Oregon. They found them offshore Northern California. Again, what could be making these landslide deposits up and down the Cascadia subduction zone? Only a large earthquake. And in these deposits, the way you look at them, it's hard to look in the seafloor. It's thousands of feet beneath the surface of the water. What we do is we collect these things called cores. It's like taking a straw from your drink, and we sink these PVC pipes. This is the PVC pipe right here. You go on a research vessel and you sink these PVC pipes and you try to collect sediment. And what you're looking for is evidence of these landslides and these sediment cores that you bring back up to the surface. Now, what is really interesting about this work is that we find evidence of at least 43 events in the last 10,000 years of these deposits of underwater landslides. And if you do the math, 43 events in 10,000 years means that it's happening roughly once every 243 years. And if you then do further math, we find that the last event was 321 years ago. You don't need to have a PhD to figure out that if the last event was 321 years ago, and they happen roughly every 243 years, one could reason we're perhaps overdue for another big event. The final piece of evidence, or one of the, sorry, not the final, but one of the other key pieces of evidence comes from historical writings. It's not all about looking for mud and doing geology. There's a lot to be said about historical accounts from people far away. This is from Japan. This is a map in Japan, which is clear across the Pacific Ocean. And there's all these accounts of a tsunami that took place up here in the north, here in the middle, and down here in the south, and further to the west. These locations are hundreds of miles apart, and yet they all saw a big tsunami. And in historical accounts of Japan, this is very precisely timed to the morning of January 28th of the year 1700. And they call it the orphan tsunami because the Japanese were very accustomed to tsunamis, but there was no shaking that accompanied the tsunami. People in Japan are used to, you feel shaking, you wait 20 or 30 or 40 minutes, and then the wave comes on shore. They were very surprised by the tsunami because there was no shaking, and yet the wave came on shore at locations very far away from each other, which is why they call this the orphan tsunami, because it lacks that parent earthquake. This has been well known in Japan, and it wasn't until Brian Atwater and others started putting together this geological evidence that it became obvious. This orphan tsunami came from us, from here, from the Pacific Northwest, traveled clear across the Pacific, and deposited its waves on the shores of Japan. And the reason it's orphaned is because the shaking that happens here is not felt there in Japan. Now, here is perhaps the most critical piece of evidence about an earthquake happening in the year 1700. It comes from something called dendrochronology, which is just the science of tree rings. Surely you've heard about this many times before. David Yamaguchi, working in the late 1990s, did this pioneering work where he went and looked at these ghost forests and figured out from the tree rings, he would take samples from the trees, and he was able to count the number of years since the trees died. And what he was able to figure out is that at many of these ghost forests, mostly on the shores of of southern Washington, that these forests, the last time they had put on new bark, fresh bark, before they all died, was between the winter of 1699 and the spring of 1700. So putting all of these things together, the story is there's no other explanation. Something big, a big earthquake that produced a lot of shaking and produced a big tsunami that traveled clear across the Pacific. It's the only way to explain all of these multiple observations. Since then, we've been able to find evidence of older earthquakes, of older tsunamis, not just the 1700 event, but an event 600 years ago, an event 1200 years ago, an event 3000 years ago, and so on. And that is what is shown here in this animation, which will start moving here in a second. What you're looking at here, every time we're coming back from the past. We started at 10,000 years in the past and we're coming towards the present. And every time a red area lights up, that is our best guess reconstruction of where and when an earthquake happened in the Pacific Northwest. Sometimes we think these earthquakes cover the entirety of Cascadia. You can see the shorelines of California, Oregon, and Washington and British Columbia up here. Sometimes the earthquakes are smaller. They can be magnitude 8s. They don't always have to cover the entire margin all the way from California to British Columbia. The number of earthquakes is called T. T12 is the 12th event before the present. This is an event 5,900 years ago. And this is our best guess of a reconstruction based on all of these things, on the offshore record of these underwater landslides, on the onshore record of these ghost forests and these tsunami deposits. There's still some errors or some uncertainties surrounding these, but we think we have a pretty good idea of the history of Cascadia of the Pacific Northwest past, which is really unique amongst the subduction zones of the world. In very few places are we able, in other places like Mexico, for example, where I come from, this kind of reconstruction is very difficult to do. It's really in the Pacific Northwest and in not many other places that we can make this kind of reconstruction. Okay, so back to Catherine Schultz and the really big one. She builds, the byline of this article also said that this is the earthquake that will destroy Seattle. So what I want to talk about next is assuming that I've convinced you that we've got a pretty good idea that something really big is possible here in the Pacific Northwest. What can we really expect if one of these really big events happened now, today? What would it look like? Well, perhaps one of the most problematic issues with earthquakes in the Pacific Northwest is unreinforced masonry. In Japan in 2011, there was a magnitude 9 earthquake, and yet there were no building collapses in that country. Magnitude 9 earthquake, about the size of what we expect here, and yet there were no building collapses there. Why? It turns out that the answer is the way we build, or the way that the Japanese build. This is an example of what an unreinforced masonry building looks like. When we say unreinforced masonry, really, we mean brick buildings built in the way in which we used to build in the 20s and 30s and 40s. Here is a movie. I'm going to play this in a second. On the left-hand side is an unreinforced masonry building. And this is a scale model. This is a full-scale model, but they put this on what is called the shake table, and they subject it to a simulated shaking from a simulated earthquake. And what you'll see is that the brick infills start to fall out. And if the brick infills fall out, then the frame of the structure is no longer strong enough to carry the entire structure and eventually collapses. There are ways to reinforce these masonry buildings, and that's what is shown here on the right. But in the Pacific Northwest, in Oregon and Washington, Northern California and British Columbia, there are still many buildings that are unreinforced. In California specifically, because of experiences with other earthquakes in the Los Angeles region especially, building brick buildings, unreinforced masonry, has been illegal for a very long time. For almost 100 years, building this way has been illegal because they learned that brick buildings do not stand earthquakes very well. So those have been illegal since 1933, and if you had a masonry building, it has been mandatory to retrofit it, to stiffen it, to make it stronger since 1986. This is an old figure, but in the Pacific Northwest, there is no legislation on unreinforced masonry buildings. And in Seattle alone, which is where statistics are the most easily available, there's about 1,000 of these buildings. Only 15% have been retrofitted, and we have reason to believe that the situation is much worse elsewhere. So that's something we can expect during the next big earthquake. Next, I'm going to talk about my area of expertise, which is tsunamis. Now, I want to talk about what a tsunami isn't. When you watch a movie, and this is a still frame I took from the movie San Andreas This is the Golden Gate building. The Marin headlands are over here down below. And this is the Presidio over here. This is not what a tsunami looks like. This is Hollywood's version of a tsunami. And you can tell that the animator who made this wasn't particularly clever, because if you look at this ship right here, it looks like all they did is they circled around it and then they copied or they cut it out and then they pasted it over here as well. That's the same identical ship in both parts of the same frame. So most of us used to think, definitely I used to think before I started my career in the earth sciences, that a tsunami looked just like a really big wave. It was just like a wind-driven wave that you can surf, except much, much, much bigger. These bluffs must be 100 or 200 feet tall. So this is really a gigantic thing. That is not what a tsunami looks like. Here's a video of what a tsunami looks like. This is Japan on March 9th of 2011. A magnitude 9 earthquake has happened 30 minutes after, before this earthquake, this video was shot. Here is a seawall, which is about 10 foot high. And this right here, this teeny tiny thing right here, that is the first arriving tsunami wave. The ocean is over here to the left. This is a port. And you can see that what has happened is the ocean has receded to the point where these vessels are now sitting on the bottom, right next to the ground. This right here is the first arriving tsunami wave, half an hour after the earthquake. And you see people are still driving around. They felt the shaking. They know that something bad has happened, but they're still driving around because they believe that this 10-foot seawall here will protect them. We fast forward 5 minutes, and now the seawater is rising rapidly. A tsunami looks a lot more like storm surge during a hurricane. Now the currents are very strong. They've pulled these ships that used to be run aground there. They've pulled these ships from their moorings. This one is capsized. And as you can see, this is quickly approaching the 10-foot level of the seawall. These people should probably not be driving there anymore. Fast forward 5 more minutes. And what you can see here is all the ships get pulled from their moorings. The ocean level continues to rise. 40 minutes is a long time, by the way. You've had 40 minutes to get out of the way. Think about that. How far away from here could you get in 40 minutes? And finally, it overtopples the seawall and chaos ensues. This is what a tsunami looks like. It's not this huge wave that just breaks over everything. It's almost a gentle giant that comes ashore. Now, the other thing that is really striking about these large tsunamis is that scenes like this aren't happening at just one location. They're happening at 500 miles of the coastline. They're happening everywhere across Japan at this point in time. Now, the other problem with tsunamis is that not only you can see this building has now been lifted off its piers and has been moved and swept away. So I visited Japan 1 year after the earthquake, and what I saw were scenes like this. This used to be all rubble right after the earthquake, and when I visited 1 year after, they cleared it all away. But I took a picture of this building because it was particularly striking to me. This building right here on the left is the same as this building right here on the right. And you can see this dangling right here. This is about 15 or 20 foot tall. This is what civil engineers call a pile. So this pile used to be 20 feet underground. It's the foundation. It's the thing that's holding this building in place. What happened during the tsunami is that the inundation was so high that the tsunami floated this building out of its piles, out of its foundation, and eventually rolled it over and deposited on its side. This is a 4-story apartment building. Scenes like this are incredibly common during these largest tsunamis. Here's another picture of a bus that was just deposited by the tsunami on the 3rd story of a building. On the left-hand side is an elementary school that you could walk through where people had to evacuate because this happened in the morning when classes were in session. So, I'm sometimes not very fun at parties because this is what I do for a living and this is what I like to talk about. I'm cognizant of that. So what I'd like to talk about now is that it's not all doom and gloom. Remember that at most places around the world, like Japan and Chile and Mexico, they've known for centuries that these big earthquakes are possible. In the Pacific Northwest, it's only in the last 30 years that we realized this was possible. So it's not all doom and gloom, I think, because I'd rather know than be surprised that these things are possible. And the fact that we now know so much about Cascadia's past means that it's time to prepare. It's time to do something about it. I'd rather not be passive and sit around waiting for this catastrophe to happen. So in the Pacific Northwest specifically, we need serious work on retrofits and building codes that make our buildings more resilient to this thing that we know is going to happen one day. Thankfully, earthquake early warning system technologies are now public, and I'll talk about this in a second. You will get alerts on your phone now before earthquake shaking, and tsunami warning in the first 5 minutes after an earthquake is quickly coming online as well. So I think even though we live in a dangerous place, there's a lot to be hopeful for. So let's talk about that. What do we do about this going forward now that we're armed with this knowledge of what is possible? The first thing, and the oldest solution in the engineering handbook, is to just make a very resilient building code. As we said, in California, building brick buildings has been illegal since 1933, and retrofitting our brick buildings has been mandatory since 1986. We need to speed up the process in the Pacific Northwest of retrofitting unreinforced masonry buildings and stiffening up our building codes. Old buildings are going to be more vulnerable, but there's no reason why every new building that we build from here on out shouldn't be able to withstand shaking. They could do it in Japan, they do it in California, why can't we do it here? The other thing is that science and technology are advancing quickly. There's many clever ways of building earthquake resilient structures, and I'd like to show you just one of them because it's so cool. This that is shown here is what is called a base isolator. This is essentially a damper, like a shock absorber, made out of rubber and lead. This is at the foundation of a building. You're underneath a building right here. And I'd like to show you a movie of how these base isolators work. This is the coolest thing I ever did as a graduate student when I was back at UC San Diego. This is a full-scale mock-up. The civil engineering department built an entire building on the shake table. I'll start this video here in a second. The shake table simulates an earthquake. This building had air conditioning. You can see the chillers up here. It had a working elevator built by the Otis elevator company. And what they did, I'll just play it. This is before they put the base isolator in. You'll see the building start to shake here in a second. They simulate earthquakes on the shake table. You can see the shaking starting here at the first floor, a little bit of motion on the third floor. I want you to focus here on the third floor. This is a simulated operating room. And as the earthquake really kicks in, you'll start to see things shaking violently. You can see the relative motion between the tan and the white parts of the building. And as you can imagine, this is not good for a building. If your building is moving like this, cracks are appearing in the concrete, pieces of concrete are spalling off. This is really, really, really bad for a building. So this simulation is of a building the way we build them today in California, at least. Now, the next video I'm going to show you is the same earthquake, but what they've done is they've installed these base isolators, these rubber dampers, right here at the foundations at the corners of the building. So let's get that video going. The motion here at the base isolator looks really dramatic, but don't look at that. Look at this operating simulated OR up here, and you'll see that even though the motion of the earthquake looks really dramatic down here, the stuff inside the operating room is barely moving. The rubber dampers are doing their job of really protecting the structure from that strong shaking. So again, down here, this looks really dramatic, like a lot of stuff is going on, but look at the things inside the building. They're barely moving. Base isolation is a very common building technique in Japan now. And in the US, it only exists in a few buildings, but there's no reason why, as we build new buildings, we shouldn't be building in this way. The other thing is earthquake early warning, and this is the other thing that our group at the University of Oregon works on extensively. We are responsible at the UO for the Oregon component of earthquake early warning. Now, what I'm going to show you here is what earthquake early warning looks like to us as academics. When we're in the lab and an earthquake happens, this is what the earthquake early warning system produces. So you'll see the earthquake starts. This is a simulation for California, and we know the earthquake starts there. And what the simulation shows is for a person there in Los Angeles, how much time there is until the earthquake hits, until you feel the shaking. So that countdown tells you 50 seconds until you feel the shaking. This up here tells you, you probably will only feel light shaking, But that's a lie, because what's happening is as the earthquake grows, new data comes in, and now we're like, oh no, shoot, it's going to be moderate shaking, and you've got about 30 seconds. As new data comes into the system, we might recalibrate and say, this wasn't really a magnitude 7.5. This earthquake is still growing. This earthquake is going to be much bigger than 7.5. And now we're forecasting strong shaking. You have about 20 seconds to do something. And this keeps going. Now 15 seconds left until the shaking, this red circle, hits this user here in Los Angeles. And now at 10 seconds or 9 seconds before the earthquake, it's now very strong shaking, and you need to take action. Now, this that I'm showing you here is what we thought earthquake early warning was going to look like. And this is still what we have in the lab. I have this running on my computer all the time. It turns out that after some research, this is so much information that regular folk, when they look at this, they're very confused by this. The countdown is confusing. The changing levels of shaking are confusing. So the system that is public now today, which is public in California, Oregon, and Washington, that system is much simpler. The way you who are listening to me will receive an earthquake early warning will look like this here in the bottom. It's going to come like an amber alert. If you've ever received an amber alert that says, be on the lookout for this Toyota Corolla vehicle with license plates, whatever, through that same system, through that same annoying sound that makes the amber alert, you will get a message that looks like this: earthquake, drop, cover, and hold on. There will be no information about how long, so you're just expected to drop, cover, and hold on and ride the earthquake out until the shaking subsides. You do not need to sign up for this service. It's already public. If you're signed up for Amber Alerts, and 99% of cell phones are signed up for Amber Alerts, you will get the alerts, so you should expect to receive this. However, if you're kind of nerdy and you want to learn more, just navigate yourselves to OregonShakeAlert.us, and there's a whole bunch of resources where you can learn about ShakeAlert and earthquake early warning. You can download specific apps that look like this on the right. So if you want that extra information about how many seconds until the strong shaking occurs, you can still get that through the apps. But the base level alert will just be something, is just now, today, will just be like this amber alert that says something big is happening, drop, cover, and hold on. So what do you do when you get an earthquake early warning in the Pacific Northwest? If you're just a regular person like you and me, get underneath your table, get underneath something sturdy, hold on, wait for the shaking to subside, and then you can exit the property. For other things that we're doing is for businesses, there's lots of stuff you can do. If you have any automated systems, you can make your automated systems respond. And this is really cool, interesting engineering. For example, you can make the elevator doors open automatically, stop the elevators at the next floor, and have the doors open so that people can get out of the elevators. Lots of companies are interacting with ShakeAlert to figure out ways in which to use the earthquake early warning. For medical services, it's obvious. If I don't want the surgeon who's got a scalpel inside of me removing my appendix to continue working as the earthquake is unfolding. For emergency responders, it turns out that simple things like opening firehouse doors. If the firehouse is damaged, and this happened in the 1994 Northridge earthquake, some of the firehouses were damaged and they couldn't open the firehouse doors and go to respond to fires and emergencies. So automated processes like that are also important. For power infrastructure, earthquake early warning can be really valuable to take the power plant offline momentarily until the shaking subsides and then bring the power plant back on. So there's lots of stuff to do. And you can expect anywhere between 5 or 10 seconds of warning, which is not that long, but in very special occasions, maybe 30, 40 seconds of warning is possible. Now, the other thing that is possible is not just the earthquake early warning, but some warning that a tsunami is going to occur from this really big earthquake. And that is also one of the key research activities that we conduct here at the UO, is how to use the same earthquake early warning information for tsunami warning. Now, it's a little different. The tsunami warnings are in charge of NOAA, that's National Oceanographic and Atmospheric Administration. And it's kind of a convoluted process. NOAA provides the warnings and forecasts to state emergency management agencies, and then the Oregon or the Washington State Emergency Management Agency distributes that warning by sirens or through other means to coastal populations. But I want to talk about this a little bit because there's just so many misconceptions about tsunamis. What is shown in this map, this is us, the Pacific Northwest, on its side. So here's California over here, This is Oregon, Washington, the Olympic Peninsula right there in British Columbia. The colors are estimates. Reality can change a little bit, but the colors are estimates of how long it will take after the earthquake for the tsunami waves to arrive on shore. Remember from that movie I showed you in Japan, it took 30, 35, or 40 minutes. In Northern California, the tsunamis can arrive in these really yellow colors. If you look at the scale up here, that means in about 10 to 12 to 15 minutes after the earthquake, they will see the first arriving tsunami waves. Here in Central Oregon, we're in this red to purple regime. So we would see 35 to 40 minutes after the earthquake, we would see the first arriving tsunami waves. Now, right here, as you go across the Olympic Peninsula, it could be almost an hour. And then once you're back into Vancouver Island, it can be as short as 10 minutes. So there's a great deal of variability, but tsunamis can take a little while after the earthquake to arrive on shore. And that's good because that gives us a lot of time to do something. So if you feel an earthquake, you don't even have to wait for somebody to tell you that there's a tsunami warning. What you need to do is know ahead of time what you're going to do. Think about it now. Where would you go if you felt shaking right now? And when you're thinking about where to go, remember, you cannot stay put. If you're in a coastal location, you cannot ride out a tsunami. With the shaking part of the earthquake, drop cover, hold on to something, and wait for the shaking to subside. But the tsunami is coming, and you can't ride it out at your house or in your apartment building by the coast. You have to know the fastest way from where you are to high ground. If you want to be kind of safe, look at a map and see where is the 30-foot contour above sea level. Where would you have to go to be 30 feet above sea level? If you want to be extremely ultra duper, super duper safe, you need to know where you have to go to be 100 feet above sea level. If you can get to 100 feet above sea level, it's very, 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 very unlikely that a tsunami will ever rise to that height. And in some places, this just isn't possible. There are very specific locations across the Oregon coast where it would take a really long time for people to find the 30-foot or the 100-foot place above sea level. So in select locations like this, we need to build specific structures called vertical evacuation structures so that people can climb up and ride out the tsunami at these vertical evacuation structures. Now, if you want to know where these places are, you can look at the Oregon Emergency Management Agency webpage. If you go to this link right here at the top, I'll leave this here in a second if you want to take a screenshot or something. In here, there's a way to access this map. And this map, you can zoom in and move around, and you can see where you would have to go to be outside of these orange and yellow regions, which are the tsunami inundation zones. So that you can start to think about and plan, where would I have to drive? Where would I have to walk? Where would I have to run in order to get out of the way? Because remember, you might have 15, 20, 30, 35 minutes to get out of the way. So once the shaking stops, get going. And that's it. That's all I have for you today. I just want to say that being ready for an earthquake involves more than just us egghead scientists that look at data and look at mud and geology in the past. We live down here at the triangle of science and technology. But if we're really going to be ready as a society, we need more than that. We need people like you to educate yourselves and educate others about what to do. And we also need very concerted and very deliberate effort from our leaders to have policy so that we can plan and prevent. We need building codes. We need vertical evacuation structures, things that can only be accomplished through organized government if we're going to withstand the next big earthquake. So thank you for joining. And Sandy, if there's time, I'm really happy to take a few questions.
Yes, there is definitely time. And we do have some questions coming in. And you say, that's it. Boy, that was a lot. There is a number of things there that I sure had no idea of. And if we've got time, I'm going to fire away some of my own questions. So actually, one of the first ones that had come in while you were speaking, we've got someone wondering if you're willing to share your slide deck. We will have the video, this recording of the presentation, but if that's okay with you,
yeah,
make that available.
Absolutely. I'm more than happy to.
Perfect. Great. We will, when we send out the notice with the video, we'll put a link to the deck or something. So the next question was, and you talked a little bit about this, the question was, are there any early warning signs that a Cascadia earthquake is imminent? And if so, what are they and how much warning time might we have?
So there's an important distinction to be made between early warning and prediction. And this is the oldest problem in seismology. Prediction means it's peacetime, everything is quiet, nothing is going on. And we can say an hour from now, a day from now, a week from now, an earthquake is going to strike offshore Newport, for example. Prediction is currently not possible. Every single seismologist in the world is working on it and wants prediction to be true, but we're really far away from being able to do that. Early warning, meanwhile, means the earthquake has just started. And because we have sensors and technology measuring the earthquake, we can tell you that the shaking that has just started is going to be really strong where you are 100 miles away from where the earthquake started. So that's why early warning only provides you 5, 10, 15, 20 seconds of warning, because we still need the earthquake to start and we need to measure it before we can tell you that the shaking is going to be strong or that the tsunami is going to be a certain height.
And as many places as you have those sensors and such, are there a lot of surprises where suddenly something pops up, an earthquake pops up, and you had no clue that that was started?
Sometimes, not in Oregon. And, you know, I have to give a lot of credit here to I'm just an academic, but at the UO, there's a group of technologists that have deployed hundreds of these sensors across Oregon. Back in 2000, there used to be 7 seismometers in the entire state of Oregon.
Wow.
Now there is about 500 of them. And that's all because of the UO and because of the support of the state government. So it's really been an incredible battle that the university and the state government have fought with the federal government to get this to be real. In some places, though, you do get surprises. Not so much here, but there was an earthquake in 2019 in California that a lot of people were surprised by. It's called the Ridgecrest earthquake. Maybe people heard about it. It was way out there in the desert, far away from the San Andreas Fault. And we were all like, we did not know that an earthquake could happen there. So it goes to show why prediction is so hard. We've only had seismometers for about 100 years, and the Earth has been around for a lot longer than that. So we're still learning about where earthquakes are possible.
It's fascinating. Okay, so this was early on in your talk, question came in, it said, it seems counterintuitive that making something stiffer produces a structure that is more resilient to an earthquake. So that reinforcement.
Yeah, thanks for that. Really what we want from the masonry, from the brick infills, is that, you know, the brick is held together by a frame. You usually have a concrete frame that's holding in the brick. We want it to not fall out of the framing. So what people usually add is like reinforced steel rebar and things like that that keep the brick from falling out of the frame. So that's probably not the best language to use. You're right. Engineers like to say that what we want to do is make the building elastic so that it's bendy with the earthquake. I guess what I mean by stiffer is just more resilient to the shaking. And you can tell that I'm a seismologist, not an engineer.
Will California fall into the sea with the big one, or Oregon, or Washington? We've heard some of those go back to the alarmist type thing. Again, we can't predict, but what do you think?
No, they're not going to fall into the sea. But I can tell you, you know, at some of these locations where we see what I'm saying subsidence, we do see that the coastline will drop. But we're talking about 1 or 2 feet, 3 feet, 4 feet, 5 feet, 6 feet would be something pretty incredible. Now, it's not going to be like the lost city of Atlantis that suddenly vanishes into the ocean depths. Now, 6 feet or 3 feet or 4 feet might not seem like a lot to you, but try to think of the energy involved in dropping every single point of the Oregon coastline and the Washington coastline by 3 or 4 feet. It's really a lot. It's more than any nuclear bomb that humanity has ever produced, and in spades. So it won't vanish into the ocean. We'll drop 4 or 5 feet into the ocean.
There's a similar question. So is everything west of I-5 really toast?
You know, a little bit, yes, but not because of the earthquake, but because we're still early on in this learning process. So when you look at California as our analog and our neighbors to the south, they've had so many damaging earthquakes going back to the 1900s and before that they've learned brick building bad, stop building brick building. Here, because it's been so quiet for so long, we're still in that process of getting ourselves acquainted with these concepts that brick building is bad. The other thing that is really bad are something called soft stories, underground garages with these flimsy columns with no sort of walls between them. Those are also known to collapse quite easily. So we're toast not because we live in a particularly dangerous place, although it is dangerous. We're toast because we're still learning how to live with this dangerous place. But once we do, like Japan, we should be just fine.
Are you able to speak to the cost involved of using or putting in the base isolator that you were talking about? I know I heard comments, and I don't know if this followed that New Yorker article, if it was something else that got people worked up, but about reinforcing the masonry, and it was so expensive that owners said they couldn't do it.
Yeah, and this is why my last slide was about how I can't do it all with the science and technology, and we need policy, and we need planning and prevention, and we need dedicated and concerted effort from our state and federal and local governments. The way it's expensive. And I'm looking at retrofits for my house right now. I'm sitting in my house and my foundation is not tied down, and it's going to cost me $5,000 to get the foundation tied down. And I don't get a tax break for doing that. In other parts of the world, like in California, when you were trying to do retrofits, you would get a tax break for doing that. You would get, the cost would be deferred. And so it's expensive, yes. It's expensive to retrofit old infrastructure, yes. So we need some way to deal with that economics. I'm not the best person to answer that question, but it has been done in other places. Again, just look at Japan, magnitude 9 earthquake, no building collapses. Are you telling me we can't do that here?
That is amazing. Along those same lines, we have a question. Have you ever considered testifying at the Oregon legislature? Thanks for the informative talk.
I haven't, but my colleague, Doug Toomey, who sits across the hall from me, he's there all the time.
Okay, we've got a question that addresses, says you focused on the hazard at the coast. Of course, that's whenever your areas of focus, but what about in the valley?
Yeah, that's a really interesting question. We don't really know. And this is a burning debate between myself and other colleagues and seismologists. We don't actually know how strong the shaking is going to be in the valley. There's going to be no impacts from the tsunami. We're too far inland. But there's a big ongoing debate as to whether the shaking is going to be just mild or whether there's a possibility of strong shaking. I personally am of the mind that the shaking is going to be strong. Especially because the valley is full of these soft sediments that are great for agriculture, but they're terrible for earthquakes. But we're still working on that. So, stay tuned. In the next 5 to 10 years, we should be able to figure that out.
Hope we don't have any big ones before we figure it out.
Me too.
Since a Cascadia earthquake doesn't have an epicenter, doesn't start all along the subduction zone at nearly, does it start all along the subduction zone at nearly the same time?
This is a great question. We talked a little bit about how big earthquakes are really big. They can span 500 miles. They do start at a point. So this is what's really confusing when you see the news. You'll see earthquake in Turkey, earthquake in Greece, Japan, Mexico, wherever, and you'll see a point on a map. Well, really, earthquakes are these really long things. The point on the map is where the earthquake started, but it takes about 2, 3, 4, 5 minutes for the entire fault to move away from the place where it starts, the epicenter. So there's still an epicenter or a hypocenter or a focus, wherever you want to call it, a place where it starts, but the part of the earth that moves is much larger than just that one point.
Yeah. So this is interesting. So we got an architect in the audience here. She said, note that because a building does not collapse does not mean it can be inhabited afterwards.
Correct.
Only that egress is possible. Yeah, just because it's standing doesn't mean it's safe. We've seen that over and over again, of course.
Right. And that should be codified in the building codes, right? So
right.
A dwelling like mine just needs to not collapse. That doesn't mean it's life safe afterwards, but it just needs to not kill me. And then,
right.
FEMA will come along and I'll be a refugee for a little while. But for other buildings like firehouses and police stations, they need to remain functional throughout the crisis. So they should be subject to a stricter building code.
Yeah. So approximately how far up the Columbia would a tsunami travel?
That's a great question. I don't know. Tsunamis don't like traveling up these narrow river inlets. But the Columbia River is a big river. So I don't know. You can look on this. I'll put this up just here for a second. If you go and look at this webpage for those that are interested, you can also navigate in this map to the Columbia River, and you can see Dogami's, our state geological agency. By the way, the governor wanted to fund Dogami. That would be a bad thing. If you wanted to look at the Dogami map, you can see how far up the Columbia River Dogami thinks there can be impacts. That's a best guess. It's very much an active research question to understand how far up Puget Sound and how far up the Columbia River we think that the tsunami can go. But you can get a rough idea by looking at these maps.
So you said that it doesn't travel up narrow areas very well, narrow waterways?
Yeah, so narrow waterway, it's really hard for tsunamis to get. They can, they just don't like to, and they don't travel very far up them.
It doesn't cause a flood and go over the edges, or does it fall apart?
It can, but it's not as impactful as up and down the coast. It depends a lot. This is why it's an active research question, because we're still trying to understand how these tsunamis interact with our coastline.
We've got somebody that looks like they're familiar with Chris Goldfinger. She commented that she thought her impression was that that Chris's recent estimate of 9+ is higher than 10% in 50 years, that it's more like 20 to 30%. Just research,
we
interpretation of the research.
Yeah, I mean, this is, you should never think that we know what we're doing. and let me qualify that statement. We know a lot, way more than we did 30 years ago. But we're trying to look into the past. We're trying to look into millennia into the past in order to come up with these estimates of how many earthquakes in the last 10,000 years. Mm-hmm. I barely remember what I was doing when I was a teenager, let alone 10,000 years ago. So it's tricky. It's tricky business. We argue a lot about whether when we find a sediment deposit, is that really an earthquake? Sometimes it's really obvious. Sometimes it's not. So there's still uncertainty as to whether there's 20 earthquakes in the last 10,000 years, 40 earthquakes in the last 10,000 years. We know there's many, but we still argue about just how many.
Many. Okay. So do you think a tsunami could travel up Puget Sound to Seattle?
It's hard for it to get all the way into Seattle, but definitely, up at that elbow on the eastern side of the Olympic Peninsula, definitely. You might see some very small impacts in Puget Sound, but it's going to be hard. But that's also an avenue of research that we're pursuing right now.
Okay. And I'm going to make one of my questions the last question, because we're almost out of time. I mentioned that I used to live in California for quite a while. I was in the Northridge earthquake. We always felt that there was a connection to the hot Santa Ana winds blowing in, that there was a heat element to it. Is there actually a weather connection?
No, there isn't.
We were so convinced.
I know. Yeah, I know. And this is one of the prevailing myths of earthquakes. As far as we can tell, rain, the weather, the Earth's crust, the deep interior of the Earth just doesn't know that that's going on, and it doesn't care.
Doesn't care. Oh. Blows our theory. Well, with that, we do need to wrap up. Thank you so much, Dr. Melgar, for taking the time to talk about your work. It is fascinating. We could probably keep going for another hour of questions. We do have a small gift of appreciation that we are going to be sending over to you. We really appreciate you taking the time, especially in the evening, to speak with us.
Thank you, Sandy.
You are welcome. Ellie, I'm going to turn it back over to you for a closing.
Yeah. So thank you to UOA PDX and all the Alumni Association members that are in the audience tonight. So we have numerous events happening throughout the year. So make sure to check your email and the website just to see what is happening. So for our gift card winners, I'm going to list them off. There's 2 of them. And then if you can send a private Q&A message with your email to the panelists, so Sandy or I, and then we can email you the link to the gift card. So the first winner is going to be James Kane, and the second one will be Ben Kersons, which if I said your name wrong, I apologize. Awesome. Well, thank you so much again for speaking, and thank you to everyone who joined tonight.